This problem, we're trying to figure out what the maximum amplitude is going to be of a spring if we just let it go. We've got this mass, it's 0.1 kilograms. We've got a spring constant K of 40 newtons per meter. And we know that the spring is going to move down to here, and then it's going to oscillate about its equilibrium position. We want to know what is that amplitude of oscillation. Now this should remind you of Bungee Barbie, because this is exactly the same thing. Right here we have UG. Right here we have US. And the two of those have to be equal to each other. This is the only kind of energy that's where the mass is when it's just hanging out at equilibrium. This is the only type of energy it has when the spring stretches its maximum distance. The amount that it stretches is X, or X max, we could think of it that way. And that is what we're looking for. We're trying to figure out how far is it going to stretch. So if we set these two things equal to each other, UG is equal to US, this is MGH, is equal to 1/2 K X max squared. But the height that this is above its furthest dropping point is X max. So H is equal to X max. Which was the trick that we needed when we were doing our Bungee Barbie. So the H and one of the X's will cancel, and we can solve for the other X. X max is going to be equal to 2mg over K. So just rearranging, that's going to give me 2 times 0.1 times 9.8 divided by 40, which is 0.049 meters. So that's part A. Part B, we're looking for sort of the period. We know how to find period. T is equal to 2 pi square root of m over k from that equation on our equation sheets. That's our period of springs. This is going to be 2 pi square root of 0.1 over 40, and that's equal to 0.314 seconds. But the question isn't asking for when it's going to do one period. It's saying we start here, it's going to go down to its lowest place, it's going to come back up to its original place, but we know that in one period it's also going to go back up and then come back down again. That one whole period is a complete oscillation. So to first get back where it starts, here, that's only going to be a half a period. So in this problem, we're looking for period over 2. So that's 0.314 divided by 2 is equal to 0.157 seconds.